Chapter 1, Section 2, Finding Limits Graphically and Numerically. Perhaps the fundamental section in Chapter 1, if not the entire book, because in this we are introduced to both an informal and a formal definition of a limit. And as I mentioned in this previous section, it's the limit process that allows us to change pre-calculus topics into calculus topics. So what we're going to do is we're going to begin by evaluating limits using estimation and either a numerical approach with a table of values or a graphical approach. So we're going to look to begin with the example here. F of x is equal to x to the third minus 8 all over x minus 2. Of course, x cannot equal 2. What I'm interested in is what happens to my function f of x. What kind of values do I get if I have x get close to 2, approach 2, but not equal to 2, because of course we know it can't equal 2. So what I did was I created a table of values, some smaller than 2, which we say values that are smaller than 2 are to the left, like on a number line, of 2, and some values greater than 2 are to the right of 2 on the number line. So we think of values from the right, from the left. And as I plugged these numbers in, all 6 of these numbers in for x in both the top and the bottom there, and simplified them, I received these values here: 10.84, 11.41, 11.9404. Now notice that the numbers are getting bigger, 11.94, and then a little bit bigger than 12.0601, 12.61, and as I get further and further away from 2, notice it gets further and further, it gets bigger and bigger, and gets further and further away from what key value right there? Well, based on this, I would say that the value is 12, because this is a little bit smaller than 12, a little bit bigger than 12. It seems like from the left, from the right, I'm approaching 12. Now, what would the graph look like? So to find the graph, I'm going to get my calculator out, and I am going to graph, and I have not taken the time to set this up, so I have to do this. So now, sorry about the delay here. Makes the video just that much longer and more difficult to sit through, but I almost have it here. And I have a TI-83 with me, so it may look a little bit different than the ones that you're using. Most are using 84s, 84 pluses, 89s, and so on. And I am going to do this in a standard graph so that I can get this. So first things first, I am going to show you that I've entered in my equation. Oh, you can't see that very well, can you? I've entered in my equation, x to the third minus 8 all over x minus 2. And then when I graph it, notice here that I get what looks a little bit like a parabola. It's not exactly a parabola in the purest sense of it's being symmetric to the y-axis, but it is indeed a parabola. And you say, well, how does this help me find the value for my limit? What's going to happen at that function when x is equal to 2? Well, that's when I would push trace, and you can see where it's at now. It's at x equals 0. You can see the x value down here. You can see the y value down here. And if I key this around to the right to make my x get bigger and bigger and bigger, now I may go off the top of my graph, but that's okay. The calculator knows all. Now notice here how close my x value is here to 2, and look at my y value. It's getting closer. It's like almost 11.5 here. It's getting closer to 12. Now if I go one more spot over, notice this is now bigger than 2, and this is bigger than 12. If I took the time to zoom in, and I'm going to zoom in here, so I'll pick the second one, and I'm going to zoom in. That's pretty close right there. So I'll hit enter again, and you can see now, and I'm going to push trace again. You can see that my x is a little bit bigger than 2, so if I come back to the left, see how much closer it is to 2? Almost there. Oh, almost. That's actually about 0.3 away, 0.03 away from 2. This is about 0.02. Look how much closer my value is to 12. So we can use the graph and we can of our calculator, and we can use this numerical approach, and we can estimate what the actual limit turns out to be. As it turns out, it is indeed 12. Now you might not know that at first, but it is indeed 12. So we start off with kind of an informal definition of what a limit is. I'm going to state this again in just a little bit. If f of x, our y value, okay, becomes arbitrarily close to a single number L. Arbitrarily close. See how I was getting closer and closer to 2 here? Getting closer and closer to 2. It becomes arbitrarily close to a single number L as x approaches c. Excuse me. This gets closer to 12 as x gets closer and closer to 2 is what I meant to say. Got that just a little mixed up. Sorry about that. And that's from either side, from numbers that are smaller from the left, numbers that are bigger from the right. Then we say the limit of our function f of x as x approaches c is equal to L. Now, this word arbitrarily is what makes this informal. We have to get something a little bit more analytical here, and that's what we're going to be working towards. Now, notice here that your function, because the numerator is a sum of cubes, that you could factor the numerator, and then look, these would cancel out. And on the slant here, I always forget to check to see if it's a slant or not, and I get x squared plus 2x plus 4. Now, this is not defined at 2, but this one is defined at 2, even though technically it's not, because it's just a variation of this. And we have the restriction here, x cannot equal 2, back way up here. But if we plug 2 in here, we did direct substitution. As x goes to 2, I would get 2 squared plus 2 times 2 plus 4, which is 4 plus 4 plus 4, which is indeed 12. So that there again, it makes me think that my limit is 12. Now, I haven't actually done anything that proved that the limit was 12. I just feel like this is a really good estimate based on the chart, based on the graph, and now based on a little bit of algebra. So we're going to go from here. We're going to get a more formal definition just a little bit. So let's look at one that maybe isn't quite as readily understood as this first one here. And let's throw a trig function in and say that g of x is equal to the sine of x over x as x goes to 0. Well, as x goes to 0, you can see x can't be 0. If x was 0, I'd have the sine of 0 over the cosine of 0. I would have the sine of 0 all over 0, which is 0 over 0. Well, that doesn't make sense. It's not undefined. It's what we call indeterminate. But we'll talk about that in a little bit. So I picked some values very close to 0 here, negative 0.3, negative 0.2, negative 0.1, and then that's from the left side, smaller, bigger numbers, 0.3, 0.2, 0.1, getting closer and closer and closer to 0. Well, look at my y values, or my g of x values. They're getting really, really, really close to what appears to be 1. So let's look at the graph now. I go back to my graph here, and I'm going to find my y equals here. Now, of course, I did not set this up ahead of time, so I messed this up mightily. And I'm waiting for my graph to get a life here. Oh, bad dog. This thing is, for whatever reason, decided to freeze on me because I decided to change the scale a little too quickly here. So let's see if I can get there. And let's go to y equals, and we'll clear this out, and we'll put the sine of x divided by x. There we go. There's the sine of x divided by x. Now, if I go to graph this, what I'm going to do is I'm going to push zoom, and I'm going to go to the trig option, 7. Okay, and as you can see here, it goes as I get closer and closer to 0 from the left side or from the right side, my y value is approaching right up here at 1. Because each one of these tick marks is worth 1. So based on this graph and based on this table, again, I would say that the limit as x goes to 0 of g of x is equal to 1. But I can't prove that other than just based on estimates. because you can't tell exactly with a graph. It's not defined at 0, so how are we supposed to know that? And I can't do anything algebraic like I did here because there's nothing that's going to factor here. So I have a couple problems that I have estimated the limits to be by using this informal definition, because I'm getting arbitrarily close to 1 as my x gets closer and closer to 0. Okay, one more guy here, and I'm going to do this all based on a graph because of the type of function it is. I have f of x is equal to 1 for x not equal to 2. I have f of x is equal to 0 for x equal to 2. So for x equal to 2, I get 0, but for everything other than 2, I get 1. So based on this graph, what would my limit be? Well, my limit as x gets closer and closer, and I'm going to write it like this for right now, as x gets closer and closer to 2, of my function f of x would be equal to 1, even though f of 2 is 0, because it's not the single point, and hopefully you'll notice here that the limit doesn't even exist, doesn't even matter, and can exist even if it's not defined at the value of c, whatever we're approaching, whatever x is approaching. So in this case, x was approaching 2, it has a completely different value. But the limit does exist, and it appears to be 1, because the closer I get from the left side or from the right side, you can see that my y values, my f of x values, are all 1. Now, as I mentioned, numerically, table, graphically, as I've done here, and analytically, that's what's coming up. We'll get to that here in just a little bit. But let's now consider examples of functions that don't have limits, where the limit fails to exist. So the first guy up is the limit as x approaches 1 of the absolute value of x minus 1 all over x minus 1. Now what's cool here, of course, x cannot equal 1. If I look at the graph here, and this is going to be a mediocre graph at best, as x approaches 1, okay, well, for any number bigger than 1, the numerator inside the absolute value bars is exactly the same as what's in the denominator. Actually, the absolute value for x bigger than 1 is going to be positive. This is going to be positive, so I am going to get 1. That's what the graph would look like. For smaller than 1, like 0.9, I'm going to get a negative in here, but the absolute value is going to be positive, but I'm going to get the negative down here, and these are going to be opposites, so that's going to be negative 1. And you can see here that this limit is not going to exist, because if you look at it from the left, you're at negative 1. If you look at it from the right, you're at positive 1. So the limit must be unique, and it's not the case here, because I get different values whether I'm approaching 1 with numbers smaller or numbers bigger. So a lot of times we'll write DNE, does not exist. And if you had to explain why, because the limit is not unique. The limit from the left does not equal the limit from the right. Now in this problem, the limit as x goes to 0, 1 over x to the 4th, holy moly, what is that going to look like? Well, graphically, it's going to look something like this. This is going to be really, really rough. So I apologize now. And as you can see here, x cannot be 0, but the limit as x approaches 0, do you see from the left side, it goes up without bound. From the right side, it goes up without bound. It's infinite. So since we do not have a unique number that it's unbounded, we say that it does not exist. Now this next one, this one's a peach. I like the graph so much, I even wrote down what you should use here as far as your scales for your x's and for your y's here. So what I'm going to do is I'm going to clear out, and I'm going to write the sine of 1 over x to the second power All right, now the importance there of the x to the second power is that no matter what you plug in for x, positive or negative, when you square it, it's going to be positive. So I'm going to be taking the signs of positive numbers. But what I want to show you here is that if I get the window just right, and my window here is negative 0.025 to 0.25 by 0.05 scale, and for the y's it's negative 1.2 to 1.2. It scales at 0.2. Watch what happens. Hopefully I entered that in correctly. No, I don't think I did the top one correctly. Let me go back up. Top one is supposed to be, oh, wait a minute, hang on. Okay, let me, here, make a quick adjustment. Okay, I think I've got that changed now. So let's go ahead and enter that in, and let's graph this. Now watch what happens with your graph. See how it's kind of bouncing back and forth there? It's kind of all over the place. What has occurred here is that as x gets closer to 0, the denominator gets really, really, really small, whether it's positive or negative, because you're squaring it. And 1 divided by really small is really big. It's going to get, this part's going to be unbounded. It's going to be getting to be bigger and bigger and bigger and bigger values. Well, the sign of bigger and bigger and bigger values doesn't get bigger and bigger. The sign, remember, goes, it oscillates back and forth between 1 and negative 1, and that's what this is trying to show you here. So again, it never approaches a single value. It's bouncing back and forth between 1 and negative 1. So even though x cannot equal 0, we would say that the limit does not exist. And if they ask you why, you could use maybe the term it oscillates. Oh, 2 L's, I think. Here it's unbounded. And here it's not unique. And those are the 3 main themes that I can think of that occur. Now I have one more function that doesn't have a limit here, because the function is defined that f of x is equal to 0 if x is a rational number, and f of x is equal to 1 if x is an irrational number. All right. Now this particular function does not have a limit for any value, because it between any two rational numbers or an infinite number of rational numbers, between any two irrational numbers and an infinite number of irrational numbers, there's not a sequence of continually getting bigger or continually getting smaller. So as we approach any value from the left or from the right, we're going to be hitting rational numbers and irrational numbers, and it's going to go back and forth between 0 and 1. So kind of the oscillation effect, but in a really weird way. Now the name of this function, it's named after a mathematician whose name I cannot pronounce. So once again, we go to Google and we ask Google to pronounce it. Dirichlet. And this is Dirichlet's function, and it's kind of an unusual one. That's why I put the little asterisk. You wouldn't be asked for anything like that based on the AP test by any means. So let me clear this out of the way, and now let's restate that informal definition. The informal definition says if f of x becomes arbitrarily close to a single number L, you know how it's a single number. You know how you can tell that L is a single number? As compared to a myriad number, it's happy. As x approaches c from either side, we say that the limit of f of x as x approaches c is equal to L. Or we use this notation, which I've already been using up above. So that's the notation you're going to get used to, need to get used to, and that stands for the limit of f of x as x approaches c is equal to L. Now, it was another mathematician that was, or is, given the credit for the more formal definition of a limit, and it's referred to as the EpsilonDelta definition. And I'm going to kind of lead into it. And by the way, Augustin Louis, or Luis, and then the last name, once again, one of those mathematicians whose last name I have been pronouncing incorrectly for quite some time. You know, listen up. Here it goes.
Koshi or Koshi.
Kushi or Koshi. So I've always called it Kashi, but Kushi formalized the definition with what we call the epsilon-delta definition. Epsilon and delta being lowercase letter Greek letters that represent typically very small numbers. And it says in the informal definition that f of x becomes arbitrarily close to L. In the more formal definition, what that means is that the difference between our function and the actual limit is very, very small, is less than epsilon. It would lie within the open interval for L minus the limit minus epsilon and the limit plus epsilon, for epsilon being a small positive number. And then the statement that x approaches C means that there exists, this is the symbol for there exists, a small positive number delta, Greek letter delta, such that x lies in the interval from the open interval from C minus delta to C, or from C to C plus delta, because again C can't be part of it. And this is stating that more formally, the difference between these x values as they approach C and the actual value of C is very small. The absolute value is very small, greater than 0 because x can't be C itself, but yet less than this small positive number delta. So that sounds kind of confusing, and I probably didn't do the greatest explanation here trying to show you how the informal matches up with the formal. The informal matches up with the formal, but now we'll go ahead and state the actual definition of a limit, the epsilon delta definition. If C and capital L are elements of the real numbers, the function f has a limit L as x approaches C if we're given any positive number epsilon. Any, we usually pick a small one. There is a positive number delta such that for all x, 0 is less than the absolute value of x minus C is less than delta, implies that the absolute value of f of x minus L is less than epsilon. So you pick an epsilon, I got to find a delta that makes that true. And if that's the case, we say that the limit as x approaches C of f of x is equal to L. Now, the epsilon delta definition is not part of the AP test that you guys will take. It's part of the BC test though. And it says, use the, in this example, just to show you one, just so that you have the opportunity to see one, although there are some in the textbook and in my notes. It says, given, we're using the epsilon delta definition to prove the following limit, that the limit as x approaches 4 of the quantity 2x minus 1 is equal to 7. All right, so this is bonus here, because even though this is the formal definition, you're not responsible for doing any problems and proving limits by using this epsilon delta definition. All right, so given an epsilon, we have to find the delta. Okay, so here's the solution. We want to show that for all epsilon greater than 0, there exists a delta greater than 0, that, see this part right here? The absolute value of 2x minus 1 quantity minus 7 is less than epsilon whenever, this part right here, 0 is less than the absolute value of x minus 4 is less than delta. This is my C, this is my f of x, this is my L. So we'll start here. We start with this. So given an epsilon, we have to find the delta. So we start with this expression. We do a little bit of algebra here, and this simplifies to this, which simplifies to this. Now remember, when you have the absolute value of a product, the absolute value of A times B is equal to the absolute value of A times the absolute value of B. So this is equal to the absolute value of 2 times the absolute value of x minus C. And of course the absolute value of 2 is 2. Well remember, this is less than epsilon. So this is less than epsilon. If I divide both sides by 2, this side and this side by 2, I get that the absolute value of x minus 4 is less than epsilon divided by 2. Well, that's this part right here. I have the absolute value of x minus 4 is less than delta. That's my epsilon over 2. That's the delta that I will find. So given any epsilon, my delta is just going to be half that number in this case. Now let's see if we can kind of show what that means. If we pick delta to be epsilon over 2, and hopefully you can see this okay. I got to make sure it's up high enough. Maybe raise it just a little bit more. There we go. If I pick delta is equal to epsilon over 2, then that means that 0 is less than the absolute value of x minus 4 is less than delta, which is equal to epsilon over 2. All right, remember now, this implies that this, which is this 2 here, and we just said that this is going to be my delta, epsilon over 2. That shows that this is less than epsilon. So if I pick values close enough, for example here, this problem right here, if I pick examples closer and closer to 4 within this interval, 4 minus delta, 4 plus delta, not equal to 4, then you can see what happens on the curve, which is actually a line, that it's in between, these values are getting closer and closer to 7. That it's between 7 plus epsilon and 7 minus epsilon. So you pick the epsilon, I have to find the delta that makes sure that it stays within this interval of values. If I can do that, then I have formally shown by definition what the limit is. And you're probably thinking to yourself right about now, I am so glad that I don't have to know this for the AP test. Well, you will see it in Calc 2, and if you take like a more rigorous class like like an advanced calculus, I think some schools offer a class called advanced calculus, you will do a lot more with epsilon delta proofs. You will see those. And of course, you will also see epsilon delta proofs in most types of analysis classes if you stick around in math long enough.